Good morning, sir. I'm Saiteja from Tribly Department. Today, AAT topic is about the compensated thermocouple ammeter. Introduction to thermocouple ammeter. Fundamental and historical context. Definition: the thermocouple ammeter measures electrical current based on heating effect of current and the thermoelectric conservation. Historical background: invented in early 20th century, widely used before modern digitometers, especially in RF and AC measurements. Working principle: current heats a resistive wire. The resulting heat generates a voltage via thermocouple proportional to current. Primary use case: ideal for measuring high frequency alternating currents where electromagnetic method. Principle of operation: heat and thermoelectric conservation in measurements. Joule's heating effect, thermocouple function, voltage current relation, heat transfer efficiency. Current passing through a resistive wire generates heat proportional to the square of the current. Thermocouple function: a thermocouple junction converts heat into measurable voltage using the Seebeck effect. Voltage current relation: the thermoelectric voltage is nonlinear related to the current, requiring calibration. Heat transfer efficiency: accuracy depends on effective thermocoupling and minimal losses of surrounding. Structure and components. Anatomy of a thermocouple ammeter. Heater wire: resistive wire through which current flows and generates heat, often made of platinum or nickel. Thermocouple junction: two dissimilar metals joined to measure temperature difference from heat generated. Thermal insulation: minimize heat losses to ensure maximum transfer to the thermocouple for accurate measurements. Mechanical housing: protective enclosure that maintains environmental stability and components alignment. Thermocompensation mechanism: ensuring accuracy amid ambient variation. Ambient temperature drift: external temperature changes can alter thermocouple voltages readings, leads to inaccurate current measurements. Reference junction control: cold junctions, ambient temperature drift reference junction controller, matched thermocouples, mechanical shielding. External temperature changes and alter thermocouple voltages reading, leading to inaccurate current measurements. Cold junctions compensation: maintains a unknown reference temperature for accurate voltage interpretation. Matched thermocouple: used for identical thermocouples for compensation, minimizes errors due to temperature variation. Mechanical shielding: enclosure reduces environmental influence, improving thermal stability. Need for compensation: why thermal drift must be managed. Thermoelectric drift, ambient variability, accuracy demand, system reliability. Superior voltage due to temperature gradients can mimic or mask actual current, including signals. Ambient variety: uncontrolled environmental causes fluctuating ambient temperature, skewing thermocouple readings. Accuracy demand: precision applications like RF testing and calibration requires error margin zero point 0.1. System reliability: compensation stabilize long-term performance, reduction recalibration frequency. Working of compensated thermocouple ammeter. Dual junction system and balancing mechanism. Dual thermocouple bridge configuration, voltage difference detection, enhanced linearity. Dual thermocouple: one junction measures the current induced heat, the other compensator for ambient temperature drift. Bridge configuration: thermocouple arranged in a differential bridge to subtract outcome thermal noise. Voltage difference detection: only the voltage difference due to current flow remains after compensation. Enhanced linearity: compensated system exhibits better linearity across current range due to reduced drift. Advantages of compensated types. Improved accuracy, compensating removes ambient induced errors, adding precious current and reading. Wide frequency range, effective in AC, DC, and RF application where electromagnetic meters fails. Thermal stability, enhanced design maintains consistent output over temperature variation. Reduced maintenance, less recalibration needed due to stability drift resistant measurement. Limitations and challenges. Drawbacks of thermocouple ammeter design. Slow response time. Thermal system reacts slower than electromagnetic types, limiting dynamic application. Nonlinear output. Thermocouple voltage is nonlinearly related to current, requiring complex calibration. Temperature dependency. Even with compensation, rescheduled temperature effect can be reached under external conditions. Mechanical sensitive thermocouple junctions are fragile and can degrade over time with repeated thermal cycling. Applications in industries: RF circuit testing, power electronics, precision instrumentation, laboratory and research. Comparison with other ammeters: electromagnetic ammeter, digital ammeter, shunt ammeter, thermocouple ammeter. Rece- Recent advances in thermocouple ammeter, digital integration, modern design includes digital display, ADC, and microcontroller for enhanced accuracy, miniaturization, compact thermocouple system suitable for embed and portable device, automated calibration, onboard electronic supports, dynamic calibration for thermal drift mitigations, improved material use of advanced alloys, increases thermal stability, and reduces noise sensitivity. Thermoelectric material used, conductors and alloys enabling precision. Nickel and aluminum, nickel-based alloys used in Type K thermal offers good stability and sensitivity. Copper and constant, widely used in Type T thermocouple for high linearity and cost efficiency. Platinum and rubidium alloys used in high precision application due to exponential stability at level temperature. Nickel acronym offers durability and consistent performance under thermal cycling conditions. Seebeck effect, voltage generation and thermal temperature gradient. Seebeck coefficient, metal dependency, nonlinear behavior, typical output ranges. Thermal time constant and dynamic. Thermal lags, time constant, mitigation strategies, dynamic range limits. These are the thermal time constant and dynamic. Calibrational technique for accuracy: current source calibration, thermal chamber testing, multi-point curve fitting, digital compensation table. Compensation circuit design. Differential configuration. Thermocouple signals are processed in a differential setup to cancel ambient drift. Cold junction reference. Electronic or physical methods maintains an unknown difference for accurate delta T readings. Bridge amplifier. Lower noise differential amplifier boosts the small thermoelectric voltage signal. Filtering and isolation. RC filters and shielding prevent EMIs from distorting thermocouple output. These are the compensation circuit design. Case study: RF circuit measurement. RF source setup. Signal generates output high frequency current to test circuits under measurement. Thermal sensing integration. Heaters wise placed in series with RF path. Thermocouple measures resulting heat. Calibration against standard reference current. Probes validates thermocouple reading across frequency range. Data logging and filtering. Digital system logs measurements and applies thermal drift correction logarithm. Comparison with Hall effect sensor. Sen- Sensing principle. Hall sensor measure magnetic field. Thermocouple detects heat from the current flow. Response time. Hall sensor responds in microsecond. Thermo lag due to heat diffusion. Frequency performance. Thermocouples are frequency dependent. Hall effect can be affected by signal shape. Application suitability. Hall sensors are best for fast and real time current sensing. Thermocouples excels in RF and high stability needed. Maintenance and longevity tips. Sensor degradation, thermal cycling waves, scheduled calibration, environmental protection. Conclusion and summary key take sub and compensator thermocouple ammeter. Thermal based measurement relies on heat from current and the Zigbee effect for indirectly at accurate current detection. Compensation is essential. Ambient temperature compensation ensures measurement accuracy along condition. Wide application spectrum used in RF labs, aerospace, power electronic due to frequency independence. Modern adoption, digital integration, miniaturization, and self-calibration sustain their relevance. Thank you.